Okay, so this is a hypothetical scenario where you have a sensor, and that sensor measurement you need to somehow store in computer memory. So it goes through this process. There is a buffer amplifier. From there will be a low pass filter. It'll go to a sample and hold amplifier. Okay, so this is pre-processing before it can go to a to D converter. Now it goes to a to D converter. And from there, you could either process it, use it in some fashion, or let's say in this case, it's just saved to computer memory. Now, when you buy a sensor, if you go shopping and you see that this happens many times and might help you in your project, which is there'll be a sensor, and I can give you an example of photoresistor. That sensor, if you buy, there will be a $1 sensor, and then there will be a $5 sensor. The question is, which one should you buy, right? If you buy the cheaper one, it'll actually be just the sensor. You have to do the data processing yourself. But if you buy the $5 one, you'll actually see that it actually has more circuitry to do things like amplification and low pass filtering. So that part will be part of the sensor. And so if you buy that $5 sensor, you will save yourself from the hassle of trying to do the amplification, which is taking the signal and magnifying it, and then perhaps filtering it. Okay, and the cheap sensor will not give you that because it doesn't have those things. So when you are buying a sensor, you want to be careful about this. The $5 is worth it. Otherwise, you'll be stuck taking the sensor, taking an op-amp, perhaps also an RC filter, putting it all together to make that thing work. And sometimes it's just not worth the effort. So then it goes to sample and hold. This is probably on the side of the Arduino. This part is on the side of the Arduino. There will be an A to D converter on the Arduino, and then you can do whatever you want with the data value. So what is here is very practical. It's useful. That's what goes on in your when you do these things with Arduino. Okay, so briefly, sensor measures physical quantity. Okay, a sensor basically is able to convert some physical phenomenon into a voltage. That's all the sensor does. So, for example, humidity, light, what else? Sound. So measures pressure, measures physical quantity, and converts to voltage. So once you have it in the world of voltages, everything boils down to using this. So you need a sensor because you need to convert from that physical quantity to something which is a voltage. Now, the buffer amplifier is something we've seen before. It's basically a non-inverting op-amp. Okay, why do we need a non-inverting op-amp. Why can't we just ignore it? One is we want to amplify sometimes. So here I've not shown resistors, but sometimes you want to put in resistors into the circuit so that it will amplify the voltage. This assuming that the sensor is giving you a large enough voltage, but it's not, then you need to put resistors to amplify. And the second thing is, so the reasons is, one is to amplify and to sort of protect the or isolate the output from input. Okay, so what if the physical quantity gives you a very large voltage? You don't want that to affect your microcontroller A to D converter. So the buffer amplifier or the amplifier acts to isolate the output to the high impedance source. Right? So it prevents your prevents any high current from seeping in. So that's the reason why you need a buffer amplifier. We have a filter, low pass filter. Now there's an assumption here. The assumption is that the thing you're measuring has high frequency noise. Assumes that Vin has high frequency noise. But that's not the case for all measurements. So some measurements, for example, if you use a accelerometer or a gyroscope, which measures the velocity, that has high frequency noise, and then you want to put a low pass filter. And we have seen a low pass filter before. An RC filter is an example of a low pass filter. So you can put that over there. Now there's one way. The other way you can do this is just forget the filter, RC filter, but just take in the input through, ignore the low pass filter, get the sample and hold, and then in software convert the high frequency, the signal into, pass it through a computational filter. That is, there is a, you could design a filter on the computer, like for example, a Butterworth filter is a low pass filter, which will get rid of noise. And then you can actually tune the frequency of the filter in code instead of trying to put a circuit, because with a circuit, once you fix the R and C, you have a cutoff frequency and you're stuck with that. But if you take this in the computer code, then you can change the frequency to suit your purposes. So you could do it both ways. Okay, once you get the filtered signal, sample and hold, amplifier. Okay, so sample and hold amplifier looks something like this, and we've talked about all these things in the past. Capacitor, this goes to an op-amp. A switch and a capacitor. And the reason why you want a sample and hold amplifier is because if you're not capturing the voltage somehow, then it's going to be lost. And so sometimes you want to hold it so that you hold it enough time that the microcontroller can process it. So holds the input for the A to D computer memory. Okay, then we have the A to D converter, which is the heart of our discussion today. It basically convert analog signal to digital signal. Okay. So this is the main important piece to actually take the data and be useful for the computer. And then if you want, you can save it to the memory.